Welcome to another video in the series about the C7000 compiler. This is the second of two videos which describe the feedback the compiler generates for a software pipelined loop. My name is George Mock and I'm your guide. As the video opens, we are looking at the assembly file generated by the compiler. This was all described and introduced in the previous video, so if that's confusing, best thing to do is to watch part 1 of the video about software pipeline feedback. And that video ended with a discussion of these lines. And now we're going to change to talking about lines at the very beginning of the software pipeline information comment block. Going to talk about these lines. So these lines right here locate the loop in the source code. That's the name of the file, and these are the line numbers of where the loop is located. The first thing to know about these lines is the term iteration count, and that is the number of times the loop executes. So the known minimum, the known maximum, pretty straightforward. Those values are not always known at compile time. They're affected by a pragma called must iterate, and there are more details about that in the video on loop optimization. Known max iteration count factor. That needs a little more explanation. It's not immediately obviously what that's about. That's the maximum number that evenly divides into the iteration count. There are instances where you may not know, say, the maximum, but you know that it's always going to be some multiple of, in this case, 256. And knowing that information, the compiler can take advantage of it to do packed data or SIMD optimizations. Back in the assembly file, we were talking about these lines. And now we're going to change focus down quite a bit to this line right here. Okay, that's what's coming up next. The minimum safe iteration count is the minimum iterations required for correct execution of the loop. We're talking about this number right here. Now that number is calculated after software pipelining is complete. So it counts in terms of the generated assembly and not the original source code, because unrolling, vectorization, and other optimizations like that can change how the generated assembly counts iterations. So this can be an odd thing to contend with, but that's how it works, okay? If the compiler is unable to guarantee a loop executes this minimum iteration count, well, then what happens is another loop gets generated. This extra loop is not software pipelining. We call it the redundant loop. In this particular example, a redundant loop does get generated, okay? And there's code before both of those loops to make the choice between which loop gets executed. There are more details about all this, including how you can avoid it and everything, in the video about redundant loops. Back in the assembly file, we were talking about this line. Now the focus changes to these lines. These lines are about a loop transformation called stage collapsing. So stage collapsing reduces the code needed for prologue or epilogue. In this particular example, it says 2 stages of the epilogue were collapsed, and so because it could do that, it moved 2 stages of the epilogue into the loop kernel, and then you increase the number of times the loop kernel runs by 2. Okay, so you can see how this overall this transformation saves code space, but it doesn't change the cycle count of the loop. Okay, because of the both of those things adjust. This can lower the minimum safe iteration count, ideally all the way down to 1. And if that happens, then your overall performance improves. Because remember, the redundant loop is not software pipeline, so it runs some 10 to 20 times slower than the software pipeline loop. So the more you can avoid executing the redundant loop, the better off you are. The ideal case is all the way down to 1. You don't have a redundant loop at all. But even if you can lower the minimum safe iteration count you're going to improve your overall performance. This last line is about load speculation. Load speculation refers to instructions that read memory but may not use it. And that can happen in connection to stage collapsing. You can put instructions, move them out of the epilogue, say, into the kernel, and that can be load instructions that are speculatively executed, that are you're reading memory and then you're not using those values that you read. Maximum amount refers to how far outside the range of normal addresses these instructions can access. So in this specific case, it says 128 bytes. So what it's saying is that with regard to the memory being accessed in this particular software pipeline loop, it could read 128 bytes before or 128 bytes after. Okay? In the video on loop optimization, I talk about the consequences of that and what to do about it. Back in the assembly file, we just got done talking about these lines, and now the focus shifts to this one line right here. This line gives a formula that estimates the total cycles required for the loop. And it's always in this a form similar to this one, some constant plus the iteration count times the II. In this case, it came to some 13 cycles times the iteration plus the iteration count times 4. We say estimate because while this is correct for the number of CPU cycles, it doesn't count cycles lost on memory effects and cache misses and that sort of thing. So it's just CPU cycles, and that's why we have to say estimate. With regard to the loop itself, this is correct for CPU cycles, but if you try and use this in a larger sense to compute the number of cycles for the entire function, that quickly becomes tricky. Because prologue and epilogue instructions often execute in parallel with other instructions from around the loop. So there can be instructions before the loop or after the loop that are executing in parallel with the prologue and epilogue instructions, and that quickly confuses things if you're trying to compute the number of CPU cycles for the entire function. So just keep in mind that this is correct in terms of CPU cycles just for the loop. Back in the assembly file, we just finished talking about this line. And now we're going to change our focus to the single scheduled iteration, which is this group of lines here. The single scheduled iteration shows all of the instructions for one iteration of the loop. And we do that because it's difficult to see any other way, because the software pipeline overlaps the iterations. Okay, so if you try and work out, well, what's going on within a single iteration, it's hard to see that. So we give it here in the software pipeline feedback comment block. Now it's called scheduled because it accounts for delays required between instructions. One example would be the MPY-WW instruction. It computes a result. You can't read that result out of the destination register for 3 cycles, and that is accounted for in the single scheduled iteration that you're looking at. I want to close this video with 2 references. The first one is to this web address here, which is a lot to type in, so an alternative is to do an internet search for C7000 compiler. All the search engines I've tried return this as the first result. This is where you go to download the compiler, access the manuals, and more details like that. The second reference is to e2e.ti.com. This is where you can go to ask any question on any TI product, including the C7000 compiler. If it is a compiler-related question, it will be answered by me. Thank you for watching this video in the series about the C7000 compiler.